Welcome to this NPTEL lecture on principles and techniques of modern radar system. We extensively use the pulse radar. So, we have seen last day the pulse Doppler radar, that actually after the phase detector what is the block diagram. Today I will I will modify the pulse radar block diagram, general block diagram I gave, that was for MTI filter. So, if we have a pulse Doppler radar, then the complete block diagram we have not seen last time, we have seen only after this. Actually that thing is valid, but the phase detector is no more there. So, I will today give that pulse Doppler radar block diagram. So, first block we have pulse train generator. Then this is put to a power amplifier. First it will put to a mixer. And also the after this there is a power amplifier, and then it is given to a duplexer. So, from the duplexer we are going to the antenna. So, this is the antenna, and here you see that we have a local oscillator at megahertz type of frequency that is giving the thing, and also we have the RF source that need not be so stable, a Klystron or nowadays TWT that will do, that is given to a multiplier, and you see that actually instead of mixer we should call this a modulator. So, pulse train generator that goes to a modulator, amplitude modulation basically with the pulse train on and off. So, pulse train generator is giving you at a PRF FR. So, it is coming, and with the power amplifier it is given to duplexer. Now, on the return path this antenna is taking. So, from duplexer the return signal. So, I will use a different signal that is taking this to the here. So, we can say that the transmitted signal was omega naught. So, this will be having a Doppler. So, omega naught plus minus omega d, that is put to a mixer, and this mixer already you see this RF is already mixed with this. So, we are having this mixture is mixed with omega naught plus omega IF. So, this will come out as omega IF plus minus omega d Doppler. Then IF amplifier, generally it is a match filter, and then we are seeing that I will erase these things. So, from this mixer we are getting this thing. So, IF amplifier is amplifying. Now, we will be having the for pulse Doppler the range gates. So, I can say range gate. I am assuming let us say we have 5 range gates. So, this is RG2, RG3, RG4, RG5. So, the whole range we are discretizing like this. So, the simultaneous by the path is there, but these range gates will be switched one by one. First the gate 1, gate 2 depending on the range. Then we have the clutter filter we are calling, it may be an MTI filter. So, range has been extracted, now clutter filter. This may be an MTI, no problem. So, this same thing has been repeated at every path. Then this clutter filter is also a narrow band filter. So, I will write that it is a narrow band filter, because now pulse shape is no more important. So, all this it can be NBF. Also before this, after range gate there can be a box cut generator as was shown earlier, that to reveal the pulse. So, this narrow band filter, and then after this as usual the detectors. Then after that there is a threshold detection to remove the various other false alarms. And so, finally, what is the outcome of this? We get a range versus velocity, a 2D map of range. One dimension is range, another dimension is the, you can say Doppler or velocity, whatever you say, range velocity. So, this is the thing with which the signal processing is done. So, the next block of a pulse Doppler is after this the signal processor. We will also see this signal processing when we will see this thing. So, this IF amplifier, this is also one processing of the signal, because correctly you will have to put this IF amplifier, usually a match filter, and this one we will see in the signal processor. So, this is the overall block diagram. You see that this after this IF amplifier we know we can get, this is our Doppler filter having, and also it is having the range information. So, this is the block diagram, this I have not given in the last class. So, this is the complete pulse radar block diagram, block diagram of pulsed Doppler radar. So, what are the salient features of this, or in which way from the earlier MTI radar diagram this is different, that let us see that difference. So, the first thing that you have noticed probably, that now there is no phase detector in the receiver chain. So, here the phase is not getting detected. So, no phase detector, and since there is no phase detector, so the concept of stello and coho, that means two stable oscillators that was there in pulse Doppler, to have the synchronization at every pulse, the phase should be precisely synchronized. So, that thing is not required. So, we can say that the fallout is no coho stello concept. So, stability is not so important from the RF oscillator. So, basically one local oscillator is there with moderate stability and RF oscillator is there in this thing. Then what we are saying clutter filter, that narrowband filter, that may be an MTI filter. So, or maybe some other design, as PRF is very high. So, first blind speed is outside the Doppler space. Now, we can say that the clutter filter may be MTI filter, may not be also, and it is, but whatever it is a narrow band that will do, no broadband filter is required, because already you have extracted the range here. Then due to high PRF, so as the pulse Doppler works on high PRF, so high PRF means lot of average signal power increases. So, high PRF says that SNR is high, SNR improves. Then, but the negative point is that high PRF means many clutters they fold over, because you are sampling. So, many clutters are fold over. So, clutter power also increases. This is also a fallout of high PRF, that clutter power increases due to the spectral fold over. But fortunately, you can use narrowband filters whose clutter rejection capability is high. You have already seen that you can have high roll up at clutter spectrum in the pass band you can employ, because all the MTI filter technology that can be utilized here. So, no problem. Then actually, since we have not with the removal of the phase detector, the coho stello concept has gone, then what limits the ability of this? Actually, the you see any oscillator will have some phase instability. So, it will have some phase noise. So, LO it will also have some, the local oscillator that will have some phase noise. So, we can say that this phase noise, LO phase noise, limits the PD's operations. So, not the clutter. Clutter can be easily removed in pulse Doppler radar, but LO phase noise is the now limiting factor. But phase noise, actually that is the detection of slow moving targets get affected due to that phase noise, because phase noise is not so high a thing, it is a short spectrum around the LO frequency. So, this LO phase noise that will affect detection of slow moving targets. That means, for small Doppler only this will affect slow moving targets. But you see, a pulse Doppler radar is never interested to have detection of slow moving targets. For that, MTI filter is a MTI radar is a better option. Its purpose is to have the high speed targets. So, it does not bother, that means LO phase noise. So now we can say that if your problem is a high speed target detection, you go for pulse Doppler radar. If you have comparatively low speed target detection, you go for MTI radar. So, this is now finally the outcome of all this discussion. Initially we said that they have ambiguity in one domain and unambiguity or certainty in other domain. So, now we are saying that this is the thing. So, you choose now that which is your interest. So, high speed target detection, if you want to detect missiles, high speed aircrafts, etc., you should have PD, and you with that you do not try to detect the low speed things that you may fall. Whether if you have low speed detection, then you forget about these high speed targets and go for MTI. This is the clear cut distinction. Okay. Now, basically the burden is now on signal processing. So, that signal processing, that means from that 2D map, how to extract, how to correct for various things, in range getting there will be some problems, etc. So, all those we will discuss in the signal processing part or in later part. So, with this I can now conclude this pulse radar thing. That means, we have seen the types of radar from the standpoint of what is the transmitter type, whether the transmitter is continuous wave or transmitter is pulsed. Now, we will go and see that another functional aspects of radar, that is from functional types. So, I will say that what a radar does. A radar basically performs one of the two functions, because you see detection, but detection after detection one is so functional types of radar types. So, first is that it detects. So, on a given a thing, it will have to first find a target. So, that is called searching operation, that you are searching for a target. So, searching is done by search radars. Now, after searching, what you will do? You will have to obviously take some action, because if there is a threat, etc., you will have to mitigate that threat. So, or in actually defense parlance they call it firefighting. So, if an enemy aircraft is coming, you will have to take action. So, that is called firefighting radar. For that, you now need to track this radar, track this target, that this object is coming. So, exactly what is its trajectory, you will have to make a track for that, and accordingly you will have to, your anti-aircraft gun should fire something, fire some thing, or you should launch a missile, etc. So, you should know the track. So, the next part is that following. So, searching is one thing, searching for a target, then you are doing that. Another job is following. Once you know, so search radar gives that information, following a moving target. You will have to follow him, you will have to gather more information from him. The radar which does that, that is called a tracking radar. So, we will discuss these two aspects of the radar one by one. First, we will see the search radar. Now, while searching, you see the who searches. Basically, radar has an antenna, that antenna is searching and that antenna is producing a beam, that beam is rotated. That rotation may be by mechanical rotation of the antenna or by electronically, but that beam rotates and you get something like in you will see whenever you go to the airport, you will see that one antenna is moving and the beam is rotating. Now, in the night sky, in the night you will see sometimes if a circus etc., they come, you can see that there is a beam which goes on. So, electromagnetic beam we cannot see, but the microwave beam, light beam fortunately we can see, but radar also does something, and if a strong echo comes, then it knows that there is something. So, search radar measures that what is the range and what is the approximately what is the location that is given to the thing. So, while searching a large volume of space needs to be covered, if the radar employs a narrow beam, then it will take a long time to search, and by the way if some high speed target comes, it will miss that. So, for searching you need a beam which is having considerably wider beam width. So, that means, this is one point, the search radar. So, the first point I will say that comparatively wider beam width, that means, so that it can search in a very fast, it can search and approximately it can find the position. Now, when it sees an echo, when it understands that okay, there is a target, now it will have to give some rough estimate of what is the position of the target. Range is one position, but you know that in a actually a radar range means it is a in spherical target, a spherical coordinate we call it the radial distance. So, r, but in a 3 dimension we require 3 coordinates. So, r is one thing, then another thing is theta, another thing is phi, 2 more angle information are required. One angle is called theta is called elevation. So, this is elevation angle and this is azimuth angle. So, we know that basically elevation means that if you have a coordinate system like this. So, if this is your z axis, now this is your range r, now this is your theta and this thing you project on the xy plane and that projection whatever angle it makes with the elevation, that is phi. So, if you give that, this point gets this point P, that uniquely gets fixed in the space. So, this azimuth and elevation, they needs to be specified by the antenna. Now, for mechanically scanned antennas, as the radar antenna scans, its beam moves across a volume of space. When a target is intercepted, the reflection returns in microseconds. Now, by that time the antenna has moved to some other position, but we can neglect that. We can say that since the antenna is not searching radar antenna is not rotating at a very fast speed and electromagnetic thing. So, typical distances in microsecond it does not move much. So, we can ignore that. Obviously, there will be a error in the measurement, but we can do that. On the other hand, if we have an electronic scanning antenna system, which is called nowadays almost the modern radars are using that electronic scanning antenna system, where the antenna is not rotated mechanically, but the phase difference between the different antenna elements are so chosen electronically that the beam itself moves. So, in that case that problem is also not there, but for mechanical nowadays in our country we most of the radars are having this mechanical system. That is why you should know that the search radar cannot measure this theta and phi very accurately. Now, when we are measuring this elevation and azimuth, the what is the actually resolution, angular resolution, that is related to the beam width, angular resolution. How? Suppose I have an antenna. Now, that let us say is producing a beam like this. So, beam width means what? This is the peak. I take two lines which are approximately, generally we call 3 dB beam width. So, from this part 3 dB down. So, this angle between these two lines, that is called the beam width theta b. So, anything within this sector theta b, we call that okay, it is in the same angle. So, resolution of an radar antenna, that is given by the beam width. Now, for search radars, this almost the beam width resolution is of the order of the beam width. But for tracking radar, actually we will see that you need much more precise information, because if you are missing this, because as the distance is in kilometers, hundreds of kilometers. So, you see that the if you miss it by small amount of error is there, then in the actual case, because we know the for a circular path, yes, the if I have a angle error of delta theta, the actual linear error will be r into delta theta. In this case, my r is very large. So, a small error here will give a large error in the position. So, that is why the tracking radar that will have several orders of magnitude less than the beam width of the antenna. Their resolution will be such. So, that is the fundamental difference between the search radar and tracking radar. That search radar more or less of the order of the beam width, usually beam width are 1 degree, 1.5 degree, 2 degree. That means, a search radar can give an angular resolution of the order of a degree, whereas a tracking radar can give you 1 by 100, but we will see a technique by which even 1 by millionth of a degree accuracy is also possible. Actually, by that way all the modern launching of various extraterrestrial spacecraft etc., landing in moon etc., that time you require that precise measurement that is done by tracking radars. So, that concept we will see in tracking radar. Actually, our main purpose of this study is to have that thing, that how if you have a beam width of theta b, you can have a accuracy of 1 by 10,000, 1 by 1 lakh, 1 by 1 million. So, that type of accuracy is possible from a technique called monopulse, which actually I ultimately will discuss in detail. But to continue the thing, that we have a search radar. So, search radar, the what is the generally you see in this all these radars for searching, they have a either they use a horn horn feed with a parabolic dish. So, there is a horn that is feeding. So, at the focus is there. So, this system, this antenna system, the parabolic dish antenna system, generally there is an at the aperture plane, there is a illumination is not kept uniform. This is done to have the side lobe levels lower. Actually, please refer to our NPTEL lectures on antenna, microwave antenna. There all these things are discussed. Just I will take those things, that what is the bandwidth of a parabolic dish with 10 dB illumination, the beam width of this dish antenna now. This is have two quantities, either 70 lambda by d or 51 lambda by d. Now, which one? That means this is wider than this. So, this is a better one. Now, if you have a 10 dB tapered illumination, that means from the center is more illuminated, and the edges of the aperture, that is illuminated 10 dB down excitation. So, in that case you will have, so I will say 10 dB taper, then you have this beam width, the whole this beam width is in degree. Please remember that this is already the radian to degree conversion taken. So, 70, where lambda it is the free space wavelength and d is the maximum dimension of the thing or the parabolic dish diameter. And if you have uniform illumination, then you have less beam width, that means that is better, but that has a problem in its side lobe. That is why always the illumination from this horn is done, design, the horn is such design that there is a taper, usually 10 dB taper is used. So, now in the H plane of the antenna, for a horn we know that for a horn fed by a rectangular guide, horn fed by rectangular waveguide, we know that in H plane the field is maximum at the center and 0 at end, something like this, and so it is a tapered illumination. So, we can say that beam width in the H plane of a horn antenna, that will be given by that 70 lambda by d, and in the E plane, the E plane we know the field structure is something like this. So, uniform. So, we can say that beam width of the horn in E plane, that will be given by 51 lambda by d. So, actually the shape of the antenna determines beam shape. A beam which is narrow in azimuth and wide in elevation, or narrow in elevation, wide in azimuth, that is called fan beam. Why we require? You see that together I cannot measure theta and phi both, elevation and azimuth. So, a such radar, what it has? It keeps two beams, two fan beams. One fan beam is, so I will say that it has two fan beams. I have already said what is a fan beam. It has narrow beam width in one direction, either in azimuth and let us say wide in elevation, or so any of the angular space it will have narrow and another one wide. So, that is called fan beam. So, two fan beams, and suppose first it tries to find an azimuth. So, it will then have a fan beam which is narrow in azimuth and wide in elevation. So, it will determine the azimuth position, then it will switch on the second fan beam which is narrow in elevation and wide in azimuth. By that it will determine the elevation information. So, by this search radar operates. So, and in certain cases you need not have any one of the information. Suppose the ship detection, suppose a ship based radar is finding the position of another ship. Now, it knows what is the elevation, because ship does not have any elevation difference, you know the elevations more or less. So, in elevation plane it does not need, so it will have a narrow azimuth beam, the fan beam needs to be narrow and it can detect. Whether whereas in the case of aircraft you cannot have that, because aircraft can have various azimuth and various elevations. So, you need to have two fan beams for these. So, in case of planes, first a narrow azimuthal fan beam is rotated through 360 degree, let us say at the most, or if you know that from which sector you have threats etc. coming or your aircraft coming, then instead of 360 some lesser angle will suffice. Then a second fan beam you can narrow in elevation, moves up and down until a target is detected at the same range at the previously acquired echo. So, you can now find second. If several targets are detected, that happens sometimes, that several targets are separated in various azimuth and elevation, several targets are detected, then they are correlated according to range. So, an azimuth echo and elevation echo, if they are having same range, then they are correlated and assumed to come from the same target. Okay. So, such radars can acquire many targets at different ranges simultaneously. On the other hand, suppose a weather radar on a plane locates storm only in the plane's path. So, it can use a narrow beam, actually in radar parlance the narrow beams are called pencil beam. So, a weather radar can have pencil beam for searching, and also it can go on tracking. So, once you are having pencil beam, basically you are doing it like a tracking radar. So, the same beam can do both the search and track operations. Okay. So, with this we conclude the topic of search radar. In the next one we will see tracking radar. Thank you.